All right, welcome to our third section in chapter 9. We're going to talk more about counting, specifically about counting disjoint sets. This is the addition rule. So in 9.2, we were counting sets where one built off the next one. This is what if I have two completely separate situations. So what if we're counting a problem and we have two sets? So we were talking about the union of sets, difference of sets, intersections of sets. These involve a little bit different situation. So first off, let's talk about what is the addition rule. If the number of elements in a union is mutually disjoint, meaning none of the sets have anything in common, then the sum of all their sets, the sum of elements in all their sets, would equal the sum of the intersection of said sets. I mean, of the union of said sets. So let me just give you a quick example of that here on the page. So suppose I have set A, and again, I don't like this. I'm not going to use this. I don't want you to use the n of A. Again, we're talking the number of sets. So if A, let's call A the set 1, 2, 3, and we'll call B the set 4, 5, 9. Then obviously A union B is going to be the set 1, 2, 3, 4, 5, 9. Because these sets have nothing in common, their union has the cardinality of their sum. Because the cardinality of B is 3, and the cardinality of A equals 3. So the cardinality of A union B equals 6. Now we're going to get to a little bit what happens when we start overlapping, because that is actually going to affect this idea and is actually one of the clear aspects of that we have to deal with. So let's do an example actually how we can use this. So how many 3-digit integers, so again we did this, are divisible by 5. So we did this previously, kind of using the where we just kind of broke it down and looked at it. But let's solve this using the addition rule. So what we're going to do is we're going to talk about the integers that are divisible by 5 either end in 5 or they end in 0. Their last digit, and I don't like that term end in, the ones digit is either 5 or 0. Thus, we can split them up into three-digit integers that are divisible by 5 by breaking them into those two sets. So if I can count how many integers, 3-digit integers end in 0, and count up how many 3-digit integers end in 5, have a ones digit of 5, then that will tell me the total. Now notice one of the key things here is this detail right here, that their intersection is the empty set. Remember, that's not 0, that's the empty set. So the key part for this to work is their intersection has to be empty. All right, so if we're doing this, then we can actually now say, well, how many 3-digit integers are there that their last digit is a 0? Well, since all digits are the 9 choices for the leftmost digit are 1 through 9, and there's 10 digits for the middle digit, then there's 9 times 10, because we would have, as it shows down here, I really like this illustration, the first digit, first spot, has 9 choices. The second digit has 10 choices. So 9 times 10 is 90. And this is actually the idea in combinatorics is the far better way to attack combinatorial problems often is to attack them and break them down. So again, we can do the same thing with 5-digit, 5 being the ones digit. We get the exact same number because again, your possible options are, so you're gonna have 3 digits, but the last one is 5. So this one's fixed. There's only one option here. This first one, because it can be 1 through 9, there are 9 different options that can go in here. And this one, though, it can be 0 through 9, so there are 10 options, which again gives us 90 options. For that, add the two sets together and you get 180. So this is just the process that we kind of can work through and understand. Now, the reason we start with adding things is because If we can add them, then we can subtract them. And again, your textbook uses notation it's about there about half the text. It's not the notation that I use, and nor do I prefer. It uses this notation for set difference, and this is I do not like this because there are operations on sets where we actually do actual subtraction. So the typically set difference is simply written as, so more accurate way to write this would be A set difference B. And again, I'm including these slides from the book because I want you to see that, because the reality is many of you are going to look at your book. When you do your homework, I can't alter how your homework types it out. And this is one of those things where there's arguments about what it is. I would actually I like your book for a lot of things. This is not one of the notation things I like it for. So I'm going to be honest with you. Now, if I have A is a finite set and B is a subset of A, so this is the key thing. So A is not only a finite set, B must be entirely contained in A. So again, using Venn diagrams, here's A, B has to be entirely inside of it. If you had a situation, so this is what we are talking about. If we had A here and B just happens to overlap it, then this formula does not work. So this formula only works in a very specific situation. Again, that's why memorizing formulas is not great, because they're very, very limited about when you can actually use them. It's better to understand why they work, by the way. Combinatorial problems are great puzzles, and the best ones are not just formulaic. Just fair warning on that one. So let's kind of illustrate this. Obviously, A can be written up into the things that are in B and the things that are, well, not in B. And that is how we get this, that we can kind of work our way back and get this idea. So let's do a different one. And this is why we can actually do some subtraction to get ourselves out of this. So we did this before. We said, what if I have 4 symbols, 26 letters, and 10 digits? And I'm doing a pin, and how many pins have at least one repeated symbol? The key part of this statement is at least one repeated symbol, which means, what if 1's repeated? What if 2's repeated? What if 3's repeated? What's 4 repeated? Obviously, the 4 repeated situation means they're all 4 the same. But we have to deal with all of those situations. So one option to answer this question literally be, how many are there with, so I'm going to count 3 sets. The number of 1 repeated, number of 2 repeated, and by the way, these can be actually really hard to do. Number of 3 repeated, and the number of 4 repeated. I could do it this way. The problem is I have to calculate each of these individually up and then add them. So that can be very, very complex. A much, much better way is, and this is the key thing, what do I not want on this question? Well, all the number of pins, remember the total number of pins, and again, it wrote it up here, but just in general, the number of pins in general was actually 36 to the 4th power. That was the total number of pins, including repetition and non-repetition. Repetition's possible, we don't have to. That's total pins. The things that I don't want are the no repeated. That was where we had 36 times 35 times 34 times 33. Remember, these are the values that we calculate out. Again, I do not recommend working on these numbers up here. It's way too easy to mistype something in it. Understanding this and understanding how to calculate it is going to be far more beneficial. So I'm just going to re-echo that over and over, because too many people approach combinatorics like, I'm going to memorize a formula. That doesn't work, because so many of these have subtle little details that if I change one detail, your formula is out the window. I'm trying to tell you this for your sake, okay? There really are great problem-solving activities. But let's come back to this. The no repetition is not what I want. So as long as I want at least one, well, that's not in there. But if I take away that, everything else is what I want. So that's why I can just subtract these, and that will give me the number of things that have at least one symbol. Because if I take away the ones that have, if I have to take all the pins and then take away the ones that have no repetition, then everything else has at least one repetition, possibly two, possibly three, possibly four. And with repetition is actually really, really hard to deal with because we haven't talked about that one. That one's actually a harder thing to deal with because if I want to do repetition, okay, so first thing I have to do is figure out which two are repeated. So I'm gonna have, I'm just gonna say there's 36 options here, one option here if this is the repeated spot, and then I would have 35 options here and 34 options here because these two are the same. Well, the problem is then that's if these two are the same. What if it's this first one and then this one? First one and the last one? What if it's the middle two that are matching? What if it's these two that are matching? What if it's these two are matching? It turns out there's 6 different ways to have done that, i.e. 3 factorial. And this is where it kind of gets funky that then you'd have to actually take that 36 times 35 times 34 times 6. And that's where these things can get really complicated really, really fast and actually become something that is really challenging. So if we're just focusing on one formula, we don't get to play with them and stop and think about this idea. All right. So again, the first answer is simply the difference of those two values. So our second question is, if all the pins are equally likely, what's the probability that random pin has at least one? Again, probability is what I want, which is going to be the difference, divided by the total possibilities, which is that 1,600,000, blah, 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 blah. So we get this thing, which is approximately 15.8%. And be very careful. When you do round, you should use approximation symbols like this symbol right here, because if you don't, you're implying that they are the same, and that's not quite work. So again, probability is what do I want over something. But this leads to an interesting idea, and that is, and this again, why, so the probability of something not happening, well, the probability of S is 1. The probability of what I don't want of A is here. So remember, I always could have taken what's the probability of having something. We got this 0.842 previously. We did the calculation, we did the probability. And in reality, we could have just taken 1 minus that. So this is the idea that probability also is what's the probability of everything happening minus the probability of what I don't want happening. The reason for this, sometimes it's easier to identify what I don't want rather than it is to identify what I do want. So be very, very careful. There's not one massive formula. Always do this. This is very much you got to pick and choose and think about it. And if you watch a video on the internet that says, always do this, I can guarantee you I can give you problems that would break their idea. So that's oversimplification, and do not do that. Think about why these things are working. What's the underlying concept? How are they piecing together? If I change a couple things, I would encourage you to do that. Some of your practice problems. I've gotten some questions about how you get better at some things. Take some of these problems and say, okay, what if I give you the same problem, but I change the question? How many pins are there that have exactly two numbers? They have exactly two repeated symbols. So in other words, they have two different symbols that are being repeated. How many different ways are there to do that? We can talk about that and just kind of go on from there. All right. So let's talk about, in general, the probability of what's called the complement of a space. In other words, the probability of what I don't want is equal to 1 minus the probability of that event actually happening. So this gets an idea in general, probability. I'm just going to kind of take away what I don't want. So let's again look at another password example. And I want you to try this one out. So I want you to go ahead and pause the video and try these 4 different questions of how many passwords are possible with 5 letters 3 through 5 letters, so we can have passwords of 3, 4, and 5 lengths, and 26 letters are your options as your alphabet for this. I know it technically is an alphabet, but it really doesn't matter. That alphabet means the sets from which I'm drawing from to create a password. All right, go ahead and pause the video and answer these questions. All right, so let's just talk about them. Let's work through each one of these and let's break it down. So the first one, we can simply look at it this way. I can have 3 spots. If I have 3 letters, that's going to be 26 times 26 times 26. So that's 26 cubed. 4 letters, it's going to be 26 times 26. Because if I don't put any restrictions, each one can have any of the 26 letters, 26 to the 4th, and obviously the same thing for the 5th. So this number right here is going to be 26 to the 5th plus 26 to the 4th plus 26 to the 3rd. So that's our first answer. All right, so that's part A. Part B, we're now asking what if no letters are repeated? Well, because no letters are repeated, it's going to force us to adjust things. So again, we have to kind of work through each of the 3 situations. So we start off with the 3 numbers here. This would be 26, but the next one would have 25 options because I cannot repeat the first letter. And then the last one have 24 options. Then this one would be very similar, but it would be 26, 25, 24. That's a 24. And then 23. And the last one would be similar, but essentially it'd be 26 factorial over 22 factorial. Sorry, 21 factorial. So I want to allow the last spot because it's going to be 21 minus 26. So let me erase this to 21. And so our answer for this problem right here is going to be the 26 factorial over 21 factorial plus 26 factorial over 22 factorial plus 26 factorial over 23 factorial. Because again, I'm simply cutting off and taking all the values from 23 down, which is 23 factorial. And so we're dividing. Recognizing that division actually is going to help you with later concepts as we build this out and understanding why different formulas actually work. All right, so let's do part C. How many different passwords have at least one repeated letter? Well, we could sit there and try to actually calculate this out. But the far better way, remember, is to simply take the answers from part A and the answers from part B, and that gives me an answer here, which is going to be the total. So then we total minus no repeat, which is going to be that 26 to the 5th plus 26 to the 4th plus 26 to the 3rd minus this whole giant thing right here. And I'm just going to write parentheses and just drop it in. So I don't make the video too long with me trying to write this down. If all the passwords equally likely, which technically they're probably not, but we can assume that much, then the likely that at least one is just going to be the total. It's going to be this number right here for part C. So that 26 to the 5th plus 26 to the 4th plus 26 to the 3rd minus I'm just doing this real quick, and we're going to have 23 factorial, 24 factorial, and actually 22 factorial, and then 21 factorial. All that over 26 to the 5th plus 26 to the 4th plus 26 to the 3rd. So again, understanding how each of these would build out is far more powerful than simply running through specific formula to kind of attack and do these different problems. And to compute this, again, we could just throw this into some kind of, often we don't actually use calculators. We use computers because all of your calculators will actually crash when you start doing these numbers. 26 factorial is actually really big. Your computer doesn't even calculate 26 factorial. What it actually does when you do 26 over 21 factorial is then computes what's left over. Your computer is designed to understand that. That's how the programming is designed. So all of you who want to be computer programmers understand that. All right, let's move on to our next one. Our next idea is actually one that sometimes students have a kind of a hard time with. It's called the principle of inclusion-exclusion. It's not really a rule, it's actually a theorem, but the idea is we want to be careful about doing certain situations. So suppose, just to give you an idea, suppose for a second, I want to know how many students in the class either are computer science majors or have a last name that starts with the letter B. Well, I can count that, and I'm gonna illustrate this before I move on. I can literally count out how many students, so how many CS students, and I could take that and I can add the how many last name starts with B. But the problem with these things is there are students who overlap in both groups. So when I counted those students up in this group and then I counted them down here, I've actually now counted those students twice. And that is where it becomes a massive problem. When we start including students twice, we actually have a hard time getting to them and understanding some different ideas. So a visualization, let's look at a Venn diagram. If I'm trying to count A union B, if I just count how many are in A and how many are in B, this is not going to work. What I'm going to get here, so if I look at this, the cardinality of A union B is equal to the cardinality of A plus the cardinality of B minus the overlap. So this would be minus A intersect B, because these are the ones that we've actually counted twice. So we counted them in A and we counted them in B. So we actually double counted them. So we have to take that back out. We actually made a mistake of just counting A plus B. And so we overcounted. What would happen for a second? And just, I'm going to use this example to kind of make this a little bit more clear. What if I drew another circle? Let's throw in C to go on top of this. C. Well, if I looked at A union B union C, let me undo that. The first thing I have to do, obviously, we're going to take this, the number of the cardinality of A plus the cardinality of B plus the cardinality of C. And then from there, we're going to subtract where the overlap. So subtract A union, sorry, not union, intersect B, subtract A intersect C, and subtract A intersect, that should be B intersect C. Well, so let's just think about this. So when I counted, let's say something was living right here. When I counted it in A, and then I counted it in C, I counted it twice, but then I took it away once. So that actually, I counted twice, I took away once, we're good. And that would work if something was also over here or over here. But what about something that lives right there in the middle? So what about something that lives in the overlap of all three of them right here? Well, I'd count it 1, 2, 3 times because I counted it A, B, and C. Then I removed it because it's actually in the intersection of A, B. It's in here. I removed it when I did the intersection of AC because it's in here. And I removed it in BC, which is here. So wait, I put it in 3 times and then I subtracted it 3 times, which means I have to actually add that in, that final intersection, A intersect B intersect C. I have to add that back in order to balance this out. So this is the principle of inclusion exclusion. And we have to be careful when we're doing this to make sure that we maximize that.